Welcome back to the Explainer. Today, we're diving into a massive, honestly pretty frustrating hurdle in the world of advanced robotics. It's a problem researchers call spatial brittleness. Look, we've got these incredibly smart robots now, right? They understand complex language, they can parse their environments, but the second they leave the pristine, perfectly calibrated conditions of a laboratory, they tend to completely fall apart. So today, we're exploring a seriously groundbreaking new framework called CamVLA that is finally freeing robots from fixed, rigid camera setups. And to really understand the scale of this problem, you just need to look at this one number, 6.3%. Imagine you have a state-of-the-art AI robot, specifically a model known as Pi 0. During training, in perfect conditions, it's a rock star. But if its observing camera gets bumped, just nudged by 15 degrees, which is a tiny shift in the real world, its ability to successfully complete a task absolutely tanks to a mere 6.3%. It basically goes blind to how its own body relates to the world, all because its perspective shifted just a tiny bit. Here's how we're going to break this down today. 1. The viewpoint trap. 2. How human vision helps. 3. The CamVLA architecture. 4. 2 specialized heads. 5. Real-world robot testing. And 6. Escaping the lab. Let's jump into Section 1. The viewpoint trap. Lab versus reality. The data here really exposes a structural crisis. When this Pi 0 model operates from its seen, canonical training viewpoint, the exact angle it's used to, it succeeds about 65.3% of the time. Pretty solid. But introduce a novel view, offset by just that 15 degrees we talked about, and boom, the success rate collapses entirely down to 6.3%. The crazy part? The scene is still completely visible, and the goal is identical, but the robot's fundamental spatial understanding just shatters. This isn't just a minor glitch. It's a huge roadblock for deploying robots in messy, unconstrained environments, where sensors constantly get bumped or held by human operators. The root cause of this massive failure comes down to what's called the hand-eye transformation. You see, standard vision-language-action models, or VLAs, are what we call base frame policies. This means the AI looks at an image from a camera, but it's forced to predict its physical movements relative to the robot's anchored base. Because of this, the neural network has to basically implicitly memorize this incredibly complex, invisible geometric math that maps the camera's perspective to the robot's base. So if that camera moves even a fraction of an inch, that memorized mapping becomes totally useless, and the action prediction completely breaks down. Which brings us to Section 2, how human vision helps a biological blueprint. Think about how you grab a cup of coffee off your desk. You don't have to do complex trigonometry, right? Your brain naturally uses two distinct systems. First, you have an egocentric action system. You decide how your hand should move directly relative to exactly what your eyes are seeing right in front of you. Second, you have an allocentric grounding system, meaning your brain just kind of intrinsically knows where your head is positioned relative to your torso. We naturally separate the question of how should I move from the question of where am I actually looking from? And it turns out this brilliant biological factorization is exactly what inspired researchers to solve this viewpoint trap for robotics. Let's see how they built that in Section 3, the CamVLA architecture, decoupling the policy. Okay, let's really unpack this pipeline. Starting on the left, the system takes in a single, standard RGB image, no fancy depth sensors required, and a natural language instruction, something like pick up the cup and place it inside the bowl. These inputs pass through an image encoder and a text tokenizer right into the central vision language model backbone. But here is where the magic actually happens. Instead of spitting out one rigid command, the flow splits into two parallel streams. The top stream is the action head. It figures out the robot's movement natively within the camera's own coordinate frame. At the exact same time, the bottom stream, the geometric head, mathematically estimates the 6 degree of freedom hand-eye matrix. Finally, these two streams converge at a deterministic geometric transformation. This translates the camera-centric action into the actual base frame action that the robot physically executes. It literally explicitly separates the action generation from the spatial geometry. Let's look closer at those streams in Section 4, two specialized heads, action and geometry. The mathematical elegance of this setup breaks down into 3 precise steps. Step 1, that action head predicts actions exactly as they appear in the visual flow. Step 2, the geometric head uses that exact same single image to regress a 6 degrees of freedom matrix, basically making a highly educated guess about the exact spatial relationship between the camera lens and the robot's physical mounting point. Step 3, the deterministic geometric transformation mathematically marries the two together. The beautiful thing here is that because the geometry is dynamically calculated on the fly by the neural network itself, human engineers don't have to manually calibrate the robot every time something moves. Notice the trajectory of the robotic gripper here, those pink and green dotted paths. By parametrizing these movements natively in the camera frame, the physical action perfectly aligns with what the system is currently looking at. The action head only cares about one thing, answering the question, how should I move to grab that cup? It creates a direct mapping between vision and action that is completely independent of where the camera happens to be floating in the room. Meanwhile, the geometric head is on a completely different mission. Its only job is to answer the second question, where am I looking from? It absorbs all the chaos, all the weird angles and viewpoint variability into one single learned pose. By treating that hand-eye transformation as an explicit variable that the AI has to continuously solve, it prevents the action controls from ever getting tangled up with the messy spatial geometry. Let's see how it holds up in reality. Section 5. Real-world robot testing, proving the concept. To really put this to the test and introduce some serious real-world chaos, the research team built this wild multi-view configuration. They mounted multiple cameras on articulated arms all around the workspace to throw extreme, totally uncalibrated viewpoint shifts at the system. The whole point was to simulate exactly what happens when a sensor drifts over time, or if you suddenly stick a robotic arm onto a new mobile base where the exact camera angle is completely unknown. And the results are pretty wild. When the camera is shifted by just 15 degrees from its training position, the state-of-the-art baselines just crumble. The Pi0 model manages a measly 16% success rate. Another top model, GR00T 1.7, drops to 14.7%. But check out CamVLA. It hits a 33% success rate. Now, while a 15-degree uncalibrated shift is notoriously brutal for any system, CamVLA stays remarkably robust. It definitively proves that dynamically inferring your geometry directly from a single RGB image absolutely crushes models that rely on rigid, assumed calibrations. You can literally see the difference in these physical rollout tests. Look at the baseline Pi0 model. When the camera angle shifts, it completely whiffs. It misses the orange block, it drops the banana entirely outside the wooden bowl, and it doesn't even come close to pinching the green cloth. Now compare that to CamVLA dealing with the exact same shifted perspectives. It seamlessly adapts. It reaches out and grabs the block, lines up the banana perfectly over the bowl, and precisely pinches the cloth. The decoupled architecture just flat out works. And we see this exact same story play out in extensive simulation environments too. The Pi0 baseline constantly struggles with spatial alignment, missing a button on a lamp, fumbling around with colored blocks, and totally failing to grasp a knife. CamVLA, on the other hand, effortlessly knocks out those exact same tasks from novel viewpoints. These simulation runs visually reinforce that CamVLA isn't just getting lucky. It consistently beats the baseline across a highly diverse set of manipulation challenges. Just to be absolutely sure this wasn't a fluke, the researchers didn't stop at testing one or two angles. They tested zero-shot generalization across incredibly dense, totally unseen viewpoints. For example, they had the robot arm interact with objects, like a green desk lamp, from completely novel angles that the model had literally never been trained on. They rigorously proved that this view robustness holds up no matter how weird or unexpected the spatial configuration gets. And we're not just talking about big, broad movements here. The system is incredibly good at precise, low-level controls. Take pushing down a specific target button on a maroon base. Even from extreme, off-center perspectives, CamVLA drives the gripper flawlessly. In fact, across all the unseen viewpoint intervals they tested, CamVLA experienced a tiny average performance drop of just 4.1%. It absolutely blew the baseline model out of the water, which suffered more than double that with an 8.9% drop. It also handles highly complex semantics without breaking a sweat. If you instruct it to slide a knife horizontally out of a wooden block and carefully place it on a cutting board, the robot needs a deep, intuitive understanding of the objects, how they work, and the exact physical trajectory needed. Once again, CamVLA manages all of this complexity flawlessly. And remember, it's doing all of this using exclusively a single monocular RGB image and a standard text command. No depth cameras, no external geometry cheats. Now, to be totally fair, no model is perfect, right? CamVLA definitely still has its limits. For instance, when trying to push a colored block into a target, it can sometimes get tripped up. The most common failure modes include self-occlusion, which is basically when the robotic arm physically gets in the way of the camera and blocks its own view of the target, or when objects are shoved right to the absolute edge of the robot's physical workspace boundaries. Honestly, understanding these boundaries is totally crucial for the next phase of making these systems even better. Which brings us to our final section, Section 6, Escaping the Lab, the Future of Robotics. At the end of the day, by replacing the fragile assumption of assumed perfect geometry with the robust discipline of learned geometry, CamVLA represents a massive leap forward. It isolates those messy viewpoint variations from the core visual action mapping, effectively closing the deployment gap that has plagued the robotics field for years.
So, I want to leave you with this thought. Think about chaotic construction sites, busy hospital wards, disaster recovery zones, or, just a really messy home kitchen. What industries are going to be completely revolutionized now that AI-driven robots no longer need perfect, static, rigorously calibrated camera conditions to actually interact with our world? When the cameras are finally free to move, the robots are finally free to step out of the lab. Thanks for joining me on this explainer. Keep learning, stay curious, and I'll catch you in the next one.